keeping up with, well, just about anything these days, it feels like trying to drink from a fire hose, doesn't it? But today we're diving into something that might sound, well, a little intimidating at first, Faraday's Law.
Yeah.
But stick with us because we're going to uncover the magic behind electromagnetism. And trust me, it's going to be a lot more fun than cracking open a physics textbook.
We're definitely going beyond the textbook for this one.
Yeah, our source today is this really amazing website. It's from Open Educational Resources, Open Source Physics at Singapore.
Okay.
And they've got this JavaScript simulation that actually lets you see Faraday's Law in action.
That's awesome.
I know, right? So we'll be talking about that in a sec. But first, just off the top of your head, what comes to mind when you hear electromagnetism?
I mean, I probably don't think about it consciously on a day-to-day basis, but it's like, it's the backbone of pretty much everything in our modern world. You know, from the power grid to your smartphone, it's all driven by electromagnetism.
Okay, yeah, that makes sense.
Yeah.
So this simulation, it features a rectangular coil rotating inside a magnetic field. I'm trying to picture it here, but why is this setup, like the setup, the key to understanding Faraday's Law?
Well, I think that rotating coil is what helps us to visualize the core concept here, which is that a changing magnetic field creates a force that can actually push electrons around and generate, electricity.
Right.
And that force is what we call an electromotive force, or EMF.
EMF, okay.
Yeah.
So it's not just like any magnetic field.
Right.
It has to be in flux.
Exactly.
To make this work.
And that's where that coil comes in. As it's spinning, the amount of magnetic field passing through it is constantly changing.
Okay.
And that's what leads to that EMF.
Okay, that's starting to click a little bit more for me now.
Yeah.
So the simulation lets you play around with, it calls it the angular frequency of the coil, how fast it's spinning. But I gotta say, angular frequency, that sounds a bit technical.
A little bit, yeah.
So in plain English, what's really going on there? And how does tweaking that affect the EMF?
Think of it like this. The faster the coil spins, the faster that magnetic field is changing, right? And the more rapidly it changes, that actually leads to a higher frequency and a larger peak EMF.
So it's like, if you shake a magnet through a coil faster, you get a stronger current.
Exactly, yeah. That's a great way to think about it.
Oh, wait, wouldn't the faster spinning also, like, create more resistance, which would then kind of, like, limit the EMF?
You're onto something there.
Oh, okay.
It's not, a limitless increase by spinning faster and faster. Factors like the resistance of the coils and the strength of that magnetic field, those all come into play.
Makes sense.
So there's always a balancing act.
Okay.
And that's something engineers have to think about when they design systems that utilize this principle.
Wow, okay. So there's more to it than just spinning things faster and faster, huh?
Yeah.
Okay, I want to go back to the big picture for a second.
Sure.
What if Faraday just hadn't stumbled across this? What would our world even look like without his discovery?
I mean, imagine a world that was primarily lit by candles with very limited mechanical power. I mean, that gives you a little glimpse into a reality without Faraday's crucial contribution.
Right.
We wouldn't have generators powering our cities. Electric motors would be a fraction of what they are today. I mean, our modern electrified world.
Right.
It just wouldn't exist as we know it.
It's kind of hard to overstate the impact of his work then.
Yeah, definitely.
And this website, with that interactive simulation, it's really helped me, at least. I can actually kind of visualize this concept.
Right.
It's not just some abstract law anymore. It's something I can almost like feel happening.
That's the power of interactive learning, right?
Yeah.
You move beyond just the theoretical.
Right.
You bring it to life.
Yeah, and I feel like we've only just kind of scratched the surface here.
Oh, absolutely.
You're saying there's more to uncover about Faraday's Law. This is getting good.
Yeah, for sure. Oh, yeah, tons more.
Okay.
We've been focusing on this rotating coil model.
Right.
Which is like a great way to grasp the basics.
Right.
But Faraday's Law, I mean, it's this fundamental principle of electromagnetism.
Okay.
It's got applications way beyond just that.
So the rotating coil is like a gateway.
Kind of, yeah.
To this whole universe of applications out there.
Exactly.
Okay. Color me intrigued. What else does Faraday's Law help us understand?
Well, okay, think about how electricity even gets to your house. Power plants use these massive generators. And guess what?
What?
They rely on Faraday's Law
Really?
to convert that mechanical energy into the electrical energy that powers our homes.
Oh, I see. So instead of like a tiny little coil,
Yeah.
it's like a giant one spinning inside a magnetic field, making enough juice for a whole city.
Exactly, yeah.
Yeah.
And then, to get that electricity to your home efficiently, we use transformers, which again rely on Faraday's law,
Oh, wow.
to either step up or step down the voltage.
Okay, that's starting to connect some dots for me.
Yeah.
But what about like wireless charging?
Yeah.
That always seems so futuristic to me. How does Faraday's law fit into that?
Oh, wireless charging is a perfect example of what we call electromagnetic induction in action.
Okay.
Think about a wireless charging pad, right?
Mm-hmm.
Your phone isn't physically plugged in,
Right.
but energy is still flowing from that pad to your phone's battery.
So there's no direct connection, but somehow energy's leaping across space.
Right.
It sounds like magic.
It might seem like magic,
Yeah.
but it's Faraday's law at work. Both the charging pad and your phone have these little coils.
Okay.
And when they're close together, the changing magnetic field from the pad's coil induces a current in your phone's coil. And that's what charges the battery.
Wow, that's pretty remarkable when you think about it.
It really is, yeah.
And to think this all started with, like, a scientist basically messing around with magnets and wires almost 200 years ago.
I know.
Okay, here's what I don't get, though. If wireless charging relies on those coils being close together,
Yeah.
how does that work for, like, electric vehicles? You can't exactly park your car on top of a charging pad, can you?
That's a great question. Wireless charging for electric vehicles actually uses a slightly different approach.
Okay.
We call it resonant inductive coupling.
Uh-huh.
It involves these carefully tuned coils
Okay.
that resonate at the same frequency,
Uh-huh.
and that allows for the energy transfer over a, slightly larger distance.
Resonant inductive coupling. I
Yeah.
feel like I'm back in physics class again.
A little bit, right?
But it's fascinating how Faraday's law is, like, finding its way into these cutting-edge technologies.
Totally.
Are there any, like, challenges with wireless charging for EVs?
Yeah.
Or is it pretty much a done deal at this point?
Well, one challenge is efficiency. The technology has gotten a lot better, but there's still some energy loss during the wireless transfer
Makes sense.
compared to, traditional plugged-in charging.
Right. Nothing's ever perfect, I guess.
Right.
But even with those challenges, it sounds like wireless charging could really, like, change how we power our devices,
Totally.
from phones to electric cars.
Absolutely.
And I guess it's not just wireless charging.
Right.
Researchers are constantly looking for new ways to use Faraday's law.
Oh, for sure.
Right. So we've gone from this simple rotating coil demo to, like, power plants,
Right.
transformers, wireless charging, who knows what else. It's like,
Yeah.
is there anything Faraday's law can't do?
Well, I wouldn't say it can do everything.
Okay, fair enough. But it's still incredible how one principle can have so many different applications.
Absolutely. And to really appreciate, how groundbreaking Faraday's discovery was, I think we need to understand a little bit about the historical context.
Oh, I love a good history lesson.
Okay, well, what's fascinating about Faraday
Yeah.
is that he didn't actually have a formal math background. He was a tinkerer, an experimenter. He really approached science from a much more, like, intuitive visual perspective.
So he wasn't a math whiz,
Right.
but he still, like, revolutionized how we think about electromagnetism.
Totally.
That's amazing.
He really did. He developed these concepts of, like, lines of force and fields, which we still use today,
Okay.
to visualize and understand how electromagnetism works. I mean, these models were incredibly groundbreaking at the time.
Right.
And they paved the way for a more, complete mathematical formulation of electromagnetism
Okay.
later on by James Clerk Maxwell.
So he was kind of a visionary then.
Totally.
Like seeing things that other people couldn't even without, like, all the fancy equations.
Yeah, absolutely. Faraday's story, I think, is a testament to the power of, observation, experimentation, and just a deep curiosity about the natural world.
It's inspiring to think that even without, a deep understanding of advanced math, someone can make such a huge impact on science.
Definitely.
Okay, we've covered so much ground here, from this simple rotating coil
Right?
to power grids, wireless charging, even a little history lesson on Faraday himself.
I know, it's been quite a journey.
But before we wrap up, is there anything else about Faraday's law that you think our listeners should really take away from all this?
There's one more really crucial aspect of Faraday's law that we haven't touched on yet.
Okay.
It's called Lenz's law.
Okay.
So Faraday's law tells us that a changing magnetic field induces an EMF.
Uh-huh.
But Lenz's law helps us figure out the direction of that induced current.
Oh, so it's not enough to know that a current is created.
Right? Okay.
We also need to know which way it's flowing.
Exactly.
And I'm guessing this is important for, like, all those real-world applications we've been talking about.
Yeah. Lenz's law essentially states that the induced current is going to flow in a direction that opposes the change in the magnetic field that produced it.
Hmm.
It's kind of like a natural feedback mechanism.
Okay, that sounds a bit counterintuitive. Why would the current oppose the very thing that created it?
Well, if you think about it in terms of energy conservation,
Okay.
if that induced current flowed in a way that actually reinforced the change in the magnetic field, you'd essentially be creating energy out of thin air,
Right.
which, violates the laws of physics.
Yeah, that's not going to fly.
Right, exactly.
Okay, that makes sense.
Yeah.
So Lenz's law makes sure the induced current acts like a brake, I guess.
Kind of, yeah.
Keeping the system from, spiraling out of control,
Exactly.
energetically speaking.
It's subtle but crucial.
Right.
And it really affects how we design and control these electromagnetic systems.
I'm learning so much today. It's amazing how even seemingly simple concepts can have so much depth and complexity when you really start to unpack them.
I know. It's pretty cool.
This deep dive has been a real eye-opener for me. Okay, so let's recap. We've gone from the simple rotating coil to power grids, wireless charging, even a history lesson on Faraday himself, then Lenz's law. It's amazing how this one, fundamental principle can just unravel into so much.
Yeah, it really is.
Before we wrap up, though, I want to kind of connect all the dots for our listeners here.
Okay.
We started by talking about how Faraday's law, at first glance, can seem a little abstract.
Right.
But this website simulation, it really helped me visualize it, at least.
I mean, yeah, it's a great tool for moving from, a theoretical understanding
Right.
to a more hands-on, grasp of what's going on.
Yeah, we talked about rotating coils, changing magnetic fields, induced currents, all that stuff.
Right.
I mean, it's not just textbook stuff anymore.
Yeah.
We even touched on the real-world applications of Faraday's law, from power generation to wireless charging for electric cars, and the challenges that come with those technologies.
And even took a little detour into the history books, right?
Right, to learn about Faraday himself, the man who, without a strong mathematical background, completely revolutionized our understanding of electromagnetism.
Through his incredible, observation and experimentation.
So if you had to pick just one takeaway you'd want our listener to walk away with today, what would it be?
I think I'd want them to understand that Faraday's law, it's not just some equation in a physics textbook,
Right.
It's this fundamental principle of nature that has profoundly shaped our world and continues to do so. It's this invisible force behind so much of our technology.
Right.
And understanding it even at a basic level, I think, gives us this deeper appreciation for how electricity and magnetism are really interconnected.
I love that. So well said. And to leave our listeners with something to ponder, we've talked about these big applications of Faraday's law.
Yeah.
But what about some everyday examples? I mean, we mentioned wireless charging, but what else is out there quietly humming along, powered by this principle?
Right.
I bet you encounter Faraday's law more than you realize, and now you have the knowledge to spot it. Until next time, keep those minds curious and stay tuned for more deep dives into the fascinating world around us.